Welcome to today's presentation, Battery Cooling Channel Optimization. My name is Mayank Vash and I'm a Senior Application Support Engineer on the HEATS Design Space Exploration team at Siemens. We will start today's presentation by discussing the motivation behind combining NX, Simcenter 3D and STAR-CCM Plus with the HEATS Design Space Exploration tool. Next, we will take a closer look at four of our Simcenter portfolio softwares: NX, STAR-CCM Plus, Simcenter 3D and HEATS. We will then explore how a NX, STAR-CCM Plus and Simcenter 3D workflow can be automated and leveraged for performing design space exploration through a battery pack optimization case study. Lastly, I'll summarize the key points and results of the case study. So without further ado, let's start with the motivation. The growth and popularity of electric vehicles is putting a spotlight on batteries. However, there are several challenges related to battery design and production, such as safety, quality, cost, durability, performance, and lightweighting, to name a few. Addressing all these challenges are critical for the battery industry to ensure a great consumer experience and adoption. One of the primary concerns in the field of battery technology is ensuring both safety and performance. To maintain optimal performance and prevent any potential hazards, it is crucial to operate battery cells within a specific temperature range. Failure to do so can result in overheating, which may lead to battery fires, posing significant risk to the consumer. Maintaining the battery temperature within tight window of optimality is difficult but crucial. In this presentation, we will explore the capabilities of Simcenter portfolio tools in finding an optimal cooling system design for battery packs. Our objective is to ensure the battery pack operates within a specified temperature range considering the electrical load cycle. Additionally, we aim to reduce the mass of the cooling system while adhering to various fluid and structural constraints. By leveraging the Simcenter portfolio suite, we can effectively address these challenges and achieve an efficient and lightweight cooling solution for battery packs. Now let's delve into the Simcenter portfolio tools that play a crucial role in building, simulating, and optimizing the battery pack model. These tools are designed to provide a comprehensive and detailed analysis of the battery pack, allowing us to assess its performance. By leveraging the capabilities of the Simcenter portfolio, we can gain valuable insights into the behavior of the battery pack, optimize its design, and ensure it meets the desired specifications. NX is Siemens' flagship computer-aided design tool. It allows you to efficiently build parametric geometries needed to perform parametric design optimization. An embedded NX Open Application Programming interface enables automatic modification and regeneration of complex geometries as parameter values are adjusted. This powerful feature ensures that design changes are seamlessly implemented throughout the model, allowing for the quick and accurate evaluation of different design scenarios. Simcenter STAR-CCM Plus is Siemens' cutting-edge computational fluid dynamic tool delivering advanced capabilities for modeling and analyzing a wide range of engineering problems. With Simcenter STAR-CCM Plus, users can effectively tackle complex scenarios involving fluid flow, heat transfer, stress, particulate flow, electromagnetics, and other related phenomena. This comprehensive safety tool empowers engineers to gain valuable insights into the behavior of fluids and their interaction with solid structures. Simcenter 3D is the most comprehensive, fully integrated CAE solution offered today. Simulation and analysis can be carried out quickly and easily with extensive geometry editing capabilities, associative simulation modeling, and multidisciplinary solutions. Here, it is used as a finite element analysis pre-processing tool and launch mechanism for the finite element solution as well. HEATS is a powerful multidisciplinary design analysis and optimization software solution that plays a crucial role in accelerating product development and reducing overall cost. By automating workflows and conducting design space exploration and optimization, HEATS streamlines the entire design process. HEATS offers several features that allow users to build simulation workflows using various commercial CAD and CAE packages. This enables automation of batch simulations, streamlining the optimization process. Users can define input parameters with specified ranges and specify the desired outputs for monitoring and/or improving performance upon. HEATS automation simplifies the process by automatically updating input files with new values from the optimization search framework, executing the entire simulation workflow, and extracting the relevant response values. These responses serve as a foundation for defining objectives and constraints for the optimization problem. Another standard feature of Heats is its unique and user-friendly optimization search framework that intelligently explores a design space by running multiple simulations with different parameter values. While the results are evaluated, local optima are defined while also searching globally for other interesting solutions. For easy interpretation and analysis of results, Heats provides a wide array of post-processing tools. These tools offer intuitive visualization capabilities, empowering engineers and designers to view high-performing designs and gain valuable insights with these. There are four key enabling technologies that makes Heats a great tool to help drive product innovation. Process automation enables the execution of CAD and CAE tools without any manual intervention. The distributed execution capabilities allows for leveraging remote HPC resources to aid in faster computation. The state-of-the-art search framework Sherpa enables efficient search with its unique hybrid adaptive techniques, and a dedicated post-processor called HeatsPost comes with several post-processing tools to help gain insights from the data generated to compare the high-performing designs discovered by Heats. Heats works seamlessly with all the major CAD and CAE tools and your internal software programs. We currently have direct portal to over 60 CAD and CAE tools consisting of Siemens as well as non-Siemens tools. Here we will focus on the NX portal, Simcenter STAR-CCM Plus portal and Simcenter 3D portal. However, it is important to note the versatility in connectivity Heats possesses to various solutions. Challenges related to design space exploration are analogous to the ones encountered during mountain climbing. When you're standing at the foot of a mountain thinking what all hurdles you might have to encounter, a natural question that arises is what tools or strategies you'll need to overcome those hurdles. With the goal to reach the summit, it can be unclear what tools are needed with limited visibility from the start point. This is exactly what traditionally is the case in conducting an optimization. After all, navigating a design landscape is like climbing a mountain where your goal is to scale a peak or a valley, only now the visibility of the terrain is even more obscured. So based upon the anticipated terrain, we are asked with picking a tool to help us achieve the summit. In case of climbing the mountain, the selection of the tool is based upon the terrain at the base of the mountain. In case of optimization, that tool is an algorithm and its setting. In reality, no single tool is typically adequate to reach the summit or in many times even makes much progress. What we really need is a Sherpa who knows all the strategies, carries all your equipment, and tailors the approach to the terrain encountered. They have done it before and can automate the journey to the summit. It also happens to be the name of the search framework deployed in Heats to help us reach our innovation goals. Sherpa is not an optimization algorithm, but rather a search framework that is based on different search strategies and algorithms. It is hybrid in nature, meaning that it contains both local and global search strategies that are working simultaneously to explore the design space. This in itself makes Sherpa a powerful toolbox for automating discovery. However, Heats is adaptive in nature as well. It is continuously learning about the design space and tuning its strategies on the fly to explore the design landscape efficiently and dynamically. There is no need for the user to perform variable screening or model simplification or any kind of algorithm selection or tuning. Users can directly set up their models and start exploring better designs faster. Sherpa allows design space exploration or specifically optimization to be deployed as part of every design problem directly by the designers or analysts responsible for making the production decisions. If you look at where simulation engineers are spending most of their time during a project, you will typically find something like this. By far, most of the time is spent in building a baseline model and running the first simulation, resulting in significant manual interaction, a lack of automation, a complexity in connecting tools and setting up the process, or oversimplification of geometry or physics to make things work, or one-off result interpretation to decide what to try next. So much time is spent such that once they get their first result, there is little time left to look at design alternatives to improve product performance before making a design decision. Perhaps they can look at a handful of manual designs at best. What's required is a solution that is built with design space exploration in mind so that it allows engineers to spend most of their time where they can extract the most value. Not on building and running that first model, but instead on exploring the design space to get the necessary insight to make better decisions much earlier in the design process. As we transform this design process, we also need alternative approaches to understanding the data generated. Now, instead of a handful of designs, we are generating hundreds or even thousands of designs alternatives. Heat's dedicated post-processor allows for automating data mining techniques that aid not only in selecting the best design for the application, but also better understanding the design domain in general. It is critical that we change the paradigm on how post-processing is conducted with the design space exploration leveraging tools and smart learning to data mine, while still presenting in an automated fashion the analysis plots we are accustomed to. With an initiative to transform data into insight, a wide variety of tools are available in HeatSpace to discover, gain insight, be equipped to make informed decisions including multiple plots type, plot synchronization, statistical methods, reduced order model generation, machine learning methods, and automated reports. Let's learn how each of these tools help transform data into insights in the subsequent topics. With an understanding of the tools to be leveraged, now let's dive into a battery pack use case to see how we can leverage heats to discover better battery pack designs faster. The objective of our study is to enhance the design of a serpentine cooling channel by minimizing the overall mass of the cooling system, which encompasses the cooling channel and coolant mass, while also ensuring a reduction in the peak cell temperature. These improvements need to be achieved while staying within the given limitations for peak cell temperature, pressure drop, and a safety factor for the structural integrity. Let us quickly familiarize ourselves with the CAD model. The battery pack model consists of 16 cylindrical cells, and each cell is 18 mm in diameter and 65 mm in height. Cells are divided into two modules that are connected in series and surrounded by the serpentine cooling channel. Each module contains two parallel strings, each containing 4 cells in series. An equivalent circuit model in Simcenter STAR-CCM Plus is used to perform the electrothermal analysis. This model is of type resistance, capacitance, resistance, and uses hybrid pulse power characterization type test data to characterize the battery cell internal behavior. To capture diffusion effects, the model uses two RC elements. To model temperature dependency accurately, the model has 4 temperature levels from 10 degrees Celsius to 50 degrees Celsius. The capacity of each cell here is 3.6 ampere hour, and ethylene glycol is used as a coolant. The parasolid geometry from Annex is imported into STAR-CCM Plus to build an automated mesh pipeline and the battery circuit model. A baseline simulation file has been created using STAR-CCM Plus for the purpose of being used as an input file in Heats. Heats via its STAR-CCM Plus portal will update the entire CAE pipeline based on the modified geometry, run the solution, and extract results in an automated way. The cooling channel is constructed with aluminum while the connectors are made of copper. Custom material properties have been assigned to the cells. To account for the dynamic nature of the system, an unsteady solution has been computed for an electrical load cycle lasting 331 seconds. Each simulation, utilizing 28 cores, takes approximately 45 minutes to complete. The temperature and pressure data obtained from STAR-CCM Plus is exported as a CSV file, facilitating its integration into the Simcenter 3D finite element model. This allows the data to be utilized as loads to conduct the thermal structural analysis, performed using the Nastran solver within Simcenter 3D. Heats will automate this step of data mapping, going from computational fluid dynamics to finite element analysis. Like the STAR-CCM Plus sim file, a baseline finite element model was built in Simcenter 3D to be used as input into Heats. The bottom edges of the channel have a fixed boundary condition, and all temperature pressure fields from STAR-CCM Plus are mapped. Heats via its Simcenter 3D portal will update the entire CAE pipeline based on the modified geometry from Annex and the updated temperature pressure fields from STAR-CCM Plus. Then run the solution and extract the results in an automated way. This study has a total of 8 variables. 2 of these variables control the width of the side and the middle portion of the channel, while the edge plane radiuses of each corner are also considered as design variables. These variables have been defined in a way that ensures the resulting channel design is symmetric. The variable wall thickness controls the thickness of the channel wall, while inlet mass flow rate controls the mass flow rate of the coolant into the channel. To achieve our goal of reducing cooling system mass and peak cell temperature, the following variable ranges were set. Updated variable values from Sherpa go in as inputs into the CAD system via the annexed CAD portal. Once the thermal computation is completed with the updated geometry, key responses including pressure drop, peak cell temperature, and coolant mass are extracted from the STAR-CCM plus simulation. Similarly, after the structural simulation is complete, the stress and channel mass are extracted from the Simcenter 3D portal. As discussed earlier, heats can communicate with different machines on the same network, allowing for utilization of remote compute resources. For this particular study, NX and Simcenter 3D were executed on the same local machine where heat study was running, while the Simcenter STAR-CCM Plus job were executed remotely on a Linux HPC in an automated fashion. Out of the 500 designs evaluated in the study, 18 designs, or approximately 4% of the total evaluated designs, resulted in errors due to failed CAD regeneration. However, it is important to note that this does not impact the heat search process, as HEATS is specifically designed to focus on high-performing design regions while efficiently navigating discontinuous design landscape. As a result of 338 feasible designs were found, representing 68% of the evaluated design. Our baseline design is infeasible as it violates the constraint on the peak cell temperature. As this is a trade-off study, it results into a Pareto front. As you can see, all designs on the Pareto front are feasible. A Pareto front represents a family of optimal solutions where competing goals are present. In this case, as we reduce the cooling system mass, the peak temperature increases and vice versa. These competing goals make this a trade-off study, and Pareto version of Sherpa was leveraged to find the optimized Pareto front. There are 31 design options to choose from on this Pareto front. Each design point on this plot represents a different level of trade-off between the maximum cell temperature and the cooling system mass. The design on this plot with the highest cell temperature has still lower temperature and mass than the baseline design. Design ID 395 has slightly lower temperature than design 434 but with a slightly higher mass. Similarly, design ID 378 has the minimum cell temperature of all the designs on the Pareto front but with highest mass. Overall, all designs on this Pareto front are feasible and better in terms of both objectives values than our baseline design. When comparing the baseline design to design 395, which lies in the middle of the Pareto front, significant changes can be observed in the wall thickness, edge plane radiuses, and inlet coolant mass flow. In terms of performance, design 395 exhibits a lower maximum cell temperature and cooling system mass compared to the baseline design. Additionally, it shows a significantly higher factor of safety and pressure drop while still satisfying the specified requirements. The parallel plot shows all objective constraints and variables on a horizontal axis, while their explored ranges during the optimization studies are shown on the vertical axis. The shaded light green portion highlights the area of the design space that are covered by the Pareto front. The wall thickness is at its minimum allowed value for all designs on the Pareto front. This parameter appears critical to performance, and it is highly probable that if we were able to reduce the wall thickness further, greater improvements may be attainable. Coolant mass flow rate is significantly higher than the baseline design for all of the Pareto front designs. Higher outer side edge plane radius is within a relatively narrow band as well. According to the Pareto influence plot, it is evident that channel wall thickness has a strong influence on both the cooling system mass and pressure drop. On the other hand, the inlet coolant mass flow rate has a strong influence on the maximum cell temperature and factor of safety, with some impact on the pressure drop. Comparatively, edge plane radiuses appear to have little to no effect when compared to other parameters. While the Pareto plot provides insights into the variable influencing the responses to determine whether the influence is positive or negative, it is necessary to examine two-dimensional relation plot. Based on the two-dimensional relation plot depicting pressure drop and cooling system mass with the color and size of the bubbles representing the wall thickness values, it is evident that there is positive correlation between wall thickness and both pressure drop and cooling system mass. This correlation aligns with the principles of physics, as reducing the channel cross-section and volume leads to higher velocities, resulting in greater pressure drop. Similarly, reducing the channel thicknesses decreases the overall mass of the channel. Similarly, from a 2D relation plot between maximum cell temperature and factor of safety, with the color and size of the bubble representing the inlet coolant mass flow rate values, it is evident that inlet coolant mass flow rate is positively correlated to the factor of safety while negatively correlated to the maximum cell temperature. From a 2D relation plot between maximum cell temperature and pressure drop, it is evident that Pareto front designs all have pressure drop close to constraint limit boundary. From this plot, we can identify design 257 as a possible design alternative. This design, while not on the Pareto front, is feasible and may be a good choice if lowering the pressure drop is an important consideration. When comparing design options, it is evident that design 257 exhibits slightly higher mass and maximum cell temperature values when compared to design 395, which is the one of the designs on the Pareto front. However, design 257 stands out with a significantly lower pressure drop. Let us now summarize key features and findings demonstrated in this case study. The virtual prototyping workflow encompassing CAD to thermal and structural simulation has been successfully developed and automated through the utilization of user-friendly NX STAR-CCM Plus and Simcenter 3D portals through HEATS. This automation ensures a seamless and efficient process, allowing for direct setup and configuration. The parallel execution capabilities and remote hardware utilization capabilities of HEATS facilitated a significantly reduced turnaround time for this design space exploration study. This allowed for faster and more efficient computation, ultimately leading to accelerated results and improved productivity. Through the utilization of HEATS, a Pareto front of designs showcasing enhanced performance in terms of both objectives was successfully discovered. These designs exhibited up to a significant 29% reduction in mass and up to a 21% decrease in maximum cell temperature as compared to the baseline design. By employing post-processing tools, we were able to identify important trends and crucial parameters that play a critical role in optimizing design performance, along with potential design alternatives. By combining HEATS with CAD and CAE tools, we were able to develop a multidisciplinary workflow, whereas high-performing battery pack designs were identified quickly and confidently. This concludes today's presentation. Please feel free to contact me if you have any questions about this application or the applicability of HEATS to your problem. Comprehensive documentation and a wide range of learning resources can be found on the Siemens Support Center as well as a dedicated HEATS customer portal. These valuable resources provide detailed information and guidance to help users effectively navigate and leverage the capabilities of HEATS. Whether you need technical documentation, tutorials, or additional support, these platforms serve as valuable knowledge hubs for all your HEATS related inquiries. Please note a new support alias in case you need to reach out to Global HEATS Support Network for support using HEATS. Thank you.